Can you see the slides?
Yes, yes.
Okay, great.
Can see. Yeah, yes. So we can wait for 2, 3 more minutes because
Yeah,
participants,
yeah, yeah.
yeah, they are,
That's fine. Thank you.
yes. Yeah, Professor Sahu, I think we can start.
Okay. So, good evening, everybody. So, today let's continue some lectures I left over last night. Actually, for you guys, this morning, right? Okay. So we talk about indirect, direct band gap, right? Indirect, direct band gap. The only difference is what? If there's we look at this K space or the momentum space, when the momentum change from the ground state to excited state, or from the valence band to the conduction band, that's called indirect. That means during the light absorption, you have to conserve the momentum. Okay, not only the energy, also momentum. Okay, that's why the indirect typically has a lower absorption coefficient because that process is more complicated. Okay, so here if you compare the inorganic semiconductors, what you see here, silicon. You guys can see my size, right? Okay, let me use a pen here. Okay, look at silicon is here, right? This plot is silicon, and germanium is here, okay? And then you have what? You have gallium arsenide, you have indium phosphide, also indium gallium arsenide, and then you see overall, if you compare silicon with gallium arsenide, right? Gallium arsenide, look at from the absorption is here, absorption coefficient is much higher, from 10 power 5 to 10 power 4. But for silicon, is what? It's 10 power 4 or 10 power 3 this period, right? See, there's a gap here. That's a gap, okay? So the same thing for germanium, with the indium gallium arsenide, right? Germanium also has a lower absorption coefficient compared to indium gallium arsenide. So basically, this silicon germanium has lower absorption coefficient because they are indirect bandgap materials. Direct, okay? And then the three compound semiconductors, they are direct bandgap. That's why the absorption is higher. Absorption coefficient is higher. What does that mean? That means, if you have the same thickness of the film to absorb sunlight, the direct bandgap absorb more sunlight. Okay, and then the right side shows also the absorption, but that's not inorganic. This organic materials. You can see, this PPV is a common materials. In early days, people use that to fabricate the polymer solar cells, so plastic solar cells. And then most of the time, these organic materials are direct bandgap materials. That's why their absorption coefficient is pretty high, 10 power 5. Okay, it's comparable with the inorganic direct bandgap materials. But organic has its own problems. Absorption is not cover the whole range. It's see here, it's kind of peak here, and then this region is it's kind of transparent. The other region is transparent. Okay. And then with that, what is absorption coefficient? How can you calculate absorption coefficient? That's basically, if you think about, if the sunlight comes with intensity I0, that lambda, when it go out with this thickness G, that light intensity change to what? I0 multiply exponential minus alpha lambda times D, okay? And then how much energy absorbed in these regions? That's basically this guy, right? You have this minus that, okay? That's basically, see here. No, this one is intensity. The top one is intensity of the light. The bottom one is called photon flux. What is photon flux? Photon flux, that's basically a number of photons per centimeter square per second, okay? That's basically how many photons you have there, per centimeter per second. Then you have this, how much incoming, and then how much go out. So total photon flux will be what? Will be this guy minus that, okay? The left one minus the right one. That's what you see. The incoming one minus the outgoing. That's how much difference that has been absorbed by these films, okay? And then if you take that to the gradients with x, because the x-axis is x, that will give you the television rate. Television rate basically is equal to what? Absorption coefficient multiplied by the photon flux. Okay, that's very basic equations. Okay. So let's talk about density of state. Why we care about density state? Because the absorption happens. You have to have the state there, right? When you promote the electrons, right, from here goes to here, and then here, there's a hole here. There's a hole here. That's basically, you have to have the state. That state to be available there so that the electron can stay there. The same thing here. This state, the hole, you have to have that state like chair there, the space for the electron or space for the hole. Okay, that's why you care about what? The density of the state. Without the density of state, even electrons promote there, but nobody accepts the electrons. Okay, that's kind of no space for the electron. That's what it means. Okay, density of state, follow these two equations. Okay, these are very basic, a lot of basic equations for semiconductors. If you guys are interested, you can read any semiconductor book to figure out. Okay. And then next thing we just talked about, right? There's a space. There's space for the electrons as a whole, but the chance for that space to be occupied by electrons, you know, is different. Okay, that's why this called, Fermi direct statistic in thermal equilibrium. That basically a different state, what is possibility for that state to be taken, to be occupied by electron. Let's follow this. Okay, that's basically follow, the energy. If you have, for example, if you have this EF, right, this is Fermi level, this is EC, this is EV, Now, of course, DC is the band, right? That means there are many states here, right? Many states. They are so close to each other. That's why they form the bands, right? Same thing here, What is this state? What is this state? Or even inside the gap, inside the gap, there's some state, some maybe trap state can take electrons. That energy E, and then the difference from there to here, that's determine how much possibility this electron occupied. That state is occupied by electron, or electron can occupy that state. So basically, you can see below EF, you can assume all the states is occupied. That's why in the what? In the valence band, all the states is occupied. The conduction band, the state is empty. Okay, that's actually follow this equation. Okay, follow this equation. So now, since we know the probability for that state to be occupied by electrons, we also know how many states there. You can see the state density multiply the probability for the state to be occupied by electrons. That tell you what? The total electron concentration in the materials. The same thing, the whole density of state, and then the whole, the state to be occupied by whole. That's basically what? It's not occupied by electron. If occupied by electron is Fe, then there's only two possibilities, right? One is occupied by electron, the other one occupied by whole, okay? So that's basically 1 minus the possibility for electron, that's the possibility or probability for the holes. That's why G, the whole, state density multiply the whole probability. And that's equal to P9. Okay, these are two equations you can use to calculate the current density under some equilibrium. And then if you look at this equation here, seems what? Complicated, right? Complicated, okay. Look like complicated, okay. That's why you can simplify this, okay. How you can simplify this? Here shows the example, okay. This 1 over E plus what? Exponential EF E minus EF over KT, right? And then if you think about conduction band, right? Conduction band is here, Fermi level is here, right? EC, EV, and since this E is exponential, when the EC minus EF is big, right? It's big. The half band gap is pretty big, right? It's big. And then this guy is much bigger than what? 1. So you can cancel 1. Okay, you can get rid of 1. So all of it stays, right? And then 1 over that exponential E minus EF over KT. That's just what? You can take this kind, inverse, right? Not inverse, opposite, right? E power minus that. That's what it. Then that's basically take this negative inside to the E minus EF. That's be EF minus E, right? Okay, this is a lowercase. Okay, lowercase f. This is the equation for to calculate the conduction band electron density. Okay, similarly, you can calculate, this is the sphere of electron. Okay, that basically tell you, this is a CB, right? This is what? VB. Okay. Then this is the equation to calculate the CB because NC multiply that, right? This is okay, back up a little bit. This is probability. This one is probability for that state to be occupied by electrons. And then here the total electron, state density, right? Density of state. And then multiply that probability. That's equal to what? Number of electrons, not number of electrons, density of electrons, right? In that materials. Similarly, you can do what? You can do for, I think this one is still what? Yeah, similarly, you can do that for valence band, okay? Valence bands, now if you look at this, right? Now is E what? EV, right? This is the EF, and this is the EC. Okay. Now you have EV minus EF, right? This EV minus EF. Now this guy is what? EV minus negative, right? Negative, that means E power some negative numbers, right? And then since this is big, right? This epsilon is big, so this one is much smaller, than 1, right? Much smaller than 1, typically you don't what? You don't just get rid of this guy. You actually use 1 minus, if you think about that, right? Like these equations, 1 over 1 plus x, that x smaller, you equal, approximately, roughly, you can see, approximately is 1 minus x. Okay, that's why it's 1 minus this guy. Okay, that's you see there. And then since what? Since this is a whole, and then that 1 minus FE is 1 minus this guy. That's equal to this. Okay, that's what you get. Now, if you know what MV, the density of state for holes, and then the probability for that density to be occupied by holes, then that's equal to MV multiplied by EXP EV minus EF over KT. Okay, that's basically tell you anything below this, how you calculate what? The P. Then the one before we talk about anything above that, you calculate N. Okay, P naught, N naught. Okay, that's under some equilibrium. So with that, I think we have developed equations, right? We just developed equation NC multiply the probability. Let's get what? The electron density. Now MV minus multiply this probability, get what? Hole density. And then you can also, rewrite this equation EF minus EC. You can see EF minus EI plus EI minus EC. With that, you can separate these two parts. This explanation two parts. This one is here, one is here. And then what you see here, one this, one this. Okay, let me remove others so that it's visible for you. And then what you get, since this part, this part can separate, become here. So the left one is back to the EI minus Z, that's NI. Okay, that's NI. And then the next part is the same, EF minus EI. Okay, and now that's what it says here. The EI typically is NC multiply this. That's the same equation as you see earlier. You see this, right? NI or PI. This I. See this I. Okay, that's the same thing. It's the same type equation. Okay. With that, typically the density of the state for holes for the conduction band is this, and density of state for holes on the valence band is that. Okay. That typically the density of space for electrons or density of space for holes. And then this equation we explained this yesterday, right? That's the basic equation shows the mass conservation. Ni squared always equal to N9 times P9. You can use that equation to find out, if you know the dopant concentration, you'll be able to find out what is the minority carrier density. So here's some questions. I'm not going to show this. I leave this question for you guys to study. You can ask questions. If you are not sure, you can ask questions during the tutoring sessions. I'm going to skip this. And then intrinsic carrier density, I think we talked about this, right? That's about 10 power, right? 10 power 10, right? Per centimeter cubic. And then you may care about, the silicon atom density, right? Say when you have atoms, come together form these single crystalline silicons. That silicon atom concentrations about 5 times 10 power, 22, Now you know that, It look like if you have 10 power 10 divided by 10 power 22, you get 10 power minus 12. That's what every 10 power 12 atoms can only contribute 1 electrons to the what as a free electron at room temperature. Okay, that's very small, right? That's why the intrinsic concentration is so small. Their conductivity is not very high. You can see there, that's so small, right? So every 10 power 13 at 10 power 12 atoms, silicon atoms can contribute only 1 free electron. Okay, I think here, we talk about that under for the intrinsic, right? The N equal to P equal to I, Ni, okay, that's equal to 10 power 10, okay? Then we typically have this equation under Sommer equilibrium. What does Sommer equilibrium mean? That means there's no bias, there's no electric bias, there's no voltage applied there. There's no optical bias. You don't shine any light on that. Okay, that's what it means. So next thing, I think I can show you a little bit about the doping. I think we have not talked about doping that. Probably we mentioned this earlier. Okay. Now the doping, if you see N-type doping, it's pretty simple, right? That basically you replace this is a phosphorus, right? You replace silicon by phosphorus. Okay. Since the silicon initially has what? Silicon has what? 4 electrons here. Okay. If you replace this by what? By phosphorus, you have 5 valence electrons. You have 1 more electron. That 1 more electrons you bring to the silicon wafer, that give you the extra reactive charge. Okay, extra reactive charge. That's why for N-type doping, you have majority carries electrons, and then hole is what? Hole is the minority carries. Now let's take example. If I dope this, if I dope my N-type is 10 power 16, right? That means N9 equal to 10 power 16, right? Then per centimeter cubic, right? And then what is the P9, right? P9 basically equal what? Because N9 times P9 equal to Ni square, right? So the P9 equal to what? Ni square over what? N9. That's Ni square is 10 power 10, right? And then you take a square of that and divide by what? N9 10 power 16. You see that 10 power 20, divided by 10 power 16, you get what? 10 power 4. You see here? 10 power 4 for what? For the whole, right? You see, the majority carrier have 10 power 16, and then the whole concentrates only 10 power 4, okay? You see how small is that, okay? That's why it's called whole is called minority, okay? The same thing you can do the p-type, p-type doping. That basically you replace the silicon this has the 4 valence electrons replaced by boron has only what? 3 electrons. Now there's it's short with 1 electron. You have hole. Okay. When you replace silicon, the silicon wafer because the boron has 1 short electron, 1 hole there. That's why you bring more positive charge there. Okay, more positive charge. Then the majority carries a hole, minority carries electrons. And that why is that? Because you still, for example, you have hole concentrations. I have boron concentration 10 power 17, right? Still my P9 is 10 power 17. And my N9 will equal to Ni square over P9, right? Over P9. Then that's 10 power 10, and then other square, and divided by 10 power 17, you get 10 power 3. You see now, the electron concentration only 10 power 3, 1000. In contrast, and then the whole concentration is 10 power 17. That's why, this 10 power 17, this 10 power 3, this is just example. That's why this is a whole is what? Electron is minority carriers and whole is majority carrier. Okay, so that's it. So with that, you can see the doping in semiconductors. Right, that's what it shows there. Okay, you have a dopant there is very close to conduction band. The electron can be easily moved from the dopant phosphorus to conduction band. The Samsung one, if you dope this with boron, that boron can easily take electron from the valence band. Okay, that's why you dope this with holes, we dope this with electrons. Okay, so that's it, right? So this is a dopant. Source of the dopant. Okay, that's how you get extra electrons there, extra hole here. Okay, so I'm going to skip this. So here there's an example here. I think I almost talk about this, right? This basically just these equations, right? If you know the dopant concentration, the dollar concentration ND, that's basically it's electron concentration. If the acceptor concentrations, if you have the acceptor, that basically tell you what is the hole concentrations. And then you can use this equation, find the minority carriers, and then find what? The conductivity, right? The conductivity basically depends by the higher concentrations of that charge, either electron or hole. That electron or hole is brought into the wafer from what? From the dopant. And then from here, I think, you can calculate this. I'm going to show this here. See, if you have the band gap, you have EI here, you have EF here. If you dope that with N-type, the EF typically get closer to EC. If you dope that beta, EF will be get closer to EV, okay? With this, you can calculate what? If the question asks you, I know Ni, I know the dopant concentration for dollar, and then I know this one is what? N9, right? N9 equal to ND 10 power 15, right? P9 will be Ni squared divided by ND. That's why 10 power 20, divided by 10 power 15, you get 10 power 5, 100,000, right? For the whole. And then what is GF minus GI? You can use this equation. How can you get this equation? You can see here, because N9 equal to Ni exponential EF minus EI over KT, right? And then, you take log on the both sides. You first move this to this side, divide by Ni, you get rid of this, N9 divided by Ni, and then you take log, you get rid of this, EF minus Z, then you move this to the left side, that's why KT times log N9 over Ni. See, KT times log ND over Ni. Because N9 is equal to ND, right? See that N9 equal to ND, okay? I get this equation. That's how you can use this equation find out the difference between the EF and the EI, okay? The EF and I. That's basically EF and I here. You find this position, okay? So that's a very simple example, show you how can you use the equation to calculate that. And then here shows, the dopant concentration than the conductivity or resistivity, right? Typically, if you have higher dopant concentrations, you bring more charge into the wafer, so you increase the conductivity, right? So if you think about the resistivity, we reduce, right? At higher dopant concentrations, you have what? Right? You have lower resistivity because you have higher conductivity, right? If you draw conductivity, it will go up. If you change this to conductivity, it will be good like that, okay? Then you can use this plot. If you know your dopant concentration, you can find the resistivity conductivity from this plot, okay? Now here's something about a lot of fully ionized. I think because the class here is very basic, I think I'm going to stop here, This will be something more advanced. We don't need to discuss. I leave these slides here so that if you are interested, you can calculate. You can read and then do the calculation. Maybe I can talk a little bit about these examples. Okay. If you see here for the heavily doping typically you dope the concentration pretty high, like 10 power 19. Okay, and then that case, it's difficult for you to use N9 Z9 because it does not follow this, equations. This equation does not follow, okay? Because they have too many there, because they are not fully ionized. And then you have to think about use this diagram. This diagram tell you, heavily doped, you will use these equations. This equation is different from the equation we talked about before, right? The reason is that only half will be ionized, okay? And then you can follow this equation. Basically, you find the difference between EF and EC. Okay, EF and EC. Typically, EF will be go above EC. Okay, go above EC. And then once you find that, you use this plot to find the data points, because these data points tell you this function. Okay, this function. Then if you find this EF minus EC, for example, is like 2 KT, and then that's it. What 2, right? 2 is somewhere here, right? 1, 2, right? And find what's this position? What is this? And then plug it back to here, and then that's how you calculate this concentration, either electron or hole. That's his example. You can figure out by itself. Then there's different slides here. I think this is more like how the effect from the temperature, from the dopant concentration, for the band gap. Then this is, I think, I will not talk about this. There's some example here. For you to calculate the N9, P9, then a few slides. So you can read this, okay? All these slides here will be the materials for you to read, okay? So with that, I think I would conclude that lectures. Okay, you guys all have the slides, right? So you should be fine. Then let's start.
Professor Chow, you are not audible. You are muted.
Oh, sorry, maybe I clicked on that. Excellent. Okay. Now, can you guys see the slides? Basically, we are talking about, we'll talk about or discuss band-to-band recombination That's called radiative. That basically you will see some photo emissions, right? Not photo emissions, light emissions. Okay, yeah, same thing. Then basically, photoluminescence, something like that. Okay, and then Auger recommendation, and then SRK, recommendation. We basically talk about these three recommendations, and then what kind of equation we can develop, to calculate these three recommendations. So first will be, I think, first question will be, what are the excess carriers, right? And then compared to what these carriers called excess areas. If you think about that, we just talk about that, right? We talk about N9, P9, right? N9, P9, right? N9, P9 is this carrier concentration under thermal equilibrium, okay? Now let's see that without any bias, without any bias. Now, if you add bias there, you will get what? Delta M, delta N, delta P. For example, then when you have the wafer shine under sunlight, you generate delta N, delta P, extra electron, extra hole. Okay, you can also inject this by applying bias, like a electric bias. You just add a voltage there, inject electron holes there, right? And then whenever you see the delta N, delta P, this is called excess carriers. Okay, excess carriers is always the extra carriers on what? On the conduction band for electrons, and the extra holes on the valence band for holes. Okay, so what are the compare? They actually compare what? So that's what. Whenever you talk about excess carrier, because you add bias there. Okay, the compare what? Compare thermal equilibrium. That's the actually N9 P9. Okay, compare N9 P9. Okay, so that's about this. What is the definition for excess carriers? Okay. So this here shows example, under thermal equilibrium, we have these equations, right? But whenever you have the light illumination, you know that N become what? N9 plus what? Delta N. And then P equal to P9 plus delta P, right? So, and then the question asks you, which is the excess carrier? That's basically what? Delta N, delta P, right? The extra carriers compared to the carrier density under thermal equilibrium. Okay, here I'm not going to talk about this because, we have very limited time to cover a lot of concept here. Okay, here shows the recommendation. Okay, whenever you have extra electrons or extra holes, because under thermal equilibrium, right, you can only hold N9, P9. Now, since you have this delta N, delta P, these are not thermal equilibrium. That means this extra charge, extra hole, extra electron, they recombine. Okay, that's why we have delta N over R. That will be the time, how long it will take, to recombine or this extra charge, excess charge, okay, excess charge, okay, excess carriers. And then if your system has lower than, for example, if this N is bigger than N9, P is bigger than P9, you have recommendation. If your system has less than N9, less than P9, okay, and then you will need to generate. The system itself will generate more carriers because they like to reach the thermal equilibrium situation. That's N9, P9, okay? So that's what it's about, okay? So here talk about the three, right? Direct band gap, recommendation, and also the treble cis recommendation. Then there's also our, that's what is that one? I almost forgot, okay? So that the other one is what? SRH, okay? SRH. And then the recommendation in semiconductors is highly nonlinear process, okay? It's very nonlinear process. So with that, now let's take a look at this. I think I already talked about that, right? When you have this N is bigger than N9, P is bigger than P9, NP bigger than N9, P9, right? You have these conditions, you have recommendation, okay? Recommendation dominant, okay? When this N9, M times P is smaller than N9, P9, or smaller than Ni squared, you have generation, okay? The system like to stay as N9, P9, okay? Whenever you have product, N times P is smaller than that, you generate more. If you're bigger than that, you recombine, and then you reach to the equilibrium, okay? So here we talk about reward bias, some equilibrium, and then the forward bias. So this is the state the system wants. So if you have the here, you need to move back to here. If you have here, you need to move back to there, okay? So that's what it's about, right? So now if you look at the example here, right? This example means, ask you, at night illuminations, which the following statement is true. So basically, under night illuminations, you have generation or recombination, especially when the light is removed. Okay, so like I can take a look at there. Now, under night, illuminations, your solar cell works as a forward bias, right? This is something we discussed yesterday. And then since you have n equal to n9 plus delta n, p is equal to p9 plus delta p, right? So your NP will be bigger than n9 p9, right? So when you remove the sunlight, right? And then the system will be go back to the left side, right? That's what, because you have extra delta n, delta p there. You have to do recombination, right? To get rid of this delta n, delta p, okay? That's just what it means, okay? So from that, you can figure out your answer here, right? When the light stops, since what? NP bigger than n 9p9, right? That's bigger than I squared, so recombination dominant, right? So answer will be A here, okay? That's the answer, okay? The same, you can do the similar things for the others slides, okay? I'm going to skip this. These are just the different examples for you to talk about that. And then let's come to here. This actually shows a lot of theory here. You see a lot of equations, but I want you to just understand this, okay? If you think about the recombination formation, right? So if you think about, anything, right? You have the electron concentration, and then you have what? You have the similar electron concentration under some equilibrium, right? If that n is bigger than that n naught, there's some mechanism for the recombination. Also, if you have, electron, you have recombination that involve, both charges, right? So here, the recombination only involve one charge. That can be electron or hole. But since here is p-type, electron is a minority, so electron dominant, right? Because electron dominant, the minority dominant. If you don't have enough electrons there, you will not be able to recombine anything. And then that one, their product, right? That means recombination require both electron and hole. The first one more like a trap, right? You just trap electrons or trap holes, right? And then the third one, if you have one electron or two holes, okay, one electron, two holes, that can impact what? The recombination. That's basically in the recombination system, I have one electron, but there's two holes involved. And then also, you can have one hole, two electron involved, okay? That's why the equation comes like this, okay? With that, you can figure out, just, this one, you can see the first one, what does it mean, right? Okay, this minority carriers density, right? The second term, what does it mean? So basically, different kind of situation that impact the recombination, either from one electron or one hole, or one electron plus one hole, or one electron plus two hole, or one hole plus two electrons. Okay, that's how that this different situation has been considered in the equation. Okay, so with that, this, right? The carrier density is equal to n9 plus delta n, p9 plus delta p equal to p. Then you have np n9 p9 is ni squared, np will be that. Then the r here is the recombination, or basically what will be delta n. See here, the delta n, right? Then you have these recombination equations, right? So if you go back here, these are general. This is the first one. It's a general. This is a general recombination equations. Then with that equations, and then you figure out the relationship between n and n9, and then delta n, delta p, and then you plug everything here, back to that equations. Then this would get these equations, okay? This equation can be very complicated. I won't just show you the process here. And then once you know that r, the recombination rate, right? Or recombination time is tau equal to delta n over r, right? R is the rate, right? This R is the rate. If I know how much extra electrons or holes I have in my systems, that extra electrons concentration divided by that rate, I get what time? I get my time, okay? With that, you can figure out that will be your new equations. And then since this is very complicated, and then you need to consider, each part, right? You have to see, you have this one term, another term, another term, right? And then typically this is another term here, the fourth term, that's from the what? from the indirect or triple cis recombination. The second term involve, N and P. This is a band-to-band recombination. The third term, these two of them together, similarly, that's actually the auger, okay? That's how you define the three different recombinations. And then the total recombination time will be equal to, tau equal to 1 divided by tau, that real 1, R1, R2, R3, okay? This is R1, let's just make up R2, R3, right? Then R1 is equal to delta N over tau 1, right? R2 is delta N over tau 2, right? That the plug there, you get the total tau, okay? That's this equation. So with that, we can basically talk about the three, type of recommendations. First, let's talk about the band-to-band, okay? Band-to-band, okay? Maybe, let's see if I have a second. I have the band-band, it should be good, okay? So you have three recommendations, right? This red to red, the radiative, auger, and SRH. Then I think we just talked about this, right? This equation we talked about earlier. You find this R1, R2, R3, okay? That's R1, R2, R3, and then, okay, and then this is R1, this R2, this R3. Okay. That's it, okay? That's basically how you get that, okay? Then let's move to the next slide. What is the band-to-band recombination? That's basically if you have what? You have electron here on the CB, you have hole on VB. Electron hole can recombine with each other and then loss of photons, right? Right. You can also do this process in opposite way. That's basically if you have photons absorbed, right? You can promote the electron to there and then leave a hole there. And then after a while, they recombine and then give you another photon back, right? That's it. So with that, since this radiative have R is equal to delta N, N9, P9 plus delta N. Okay, that's how you have delta N divided by that, you get the 1 over B N9, P9 plus delta N. This B depends on materials. Different materials have different coefficient for the band-to-band absorption. Okay, and then if you talk about that, B times that N9 MP minus N9 P9, how you get this? That's from here. Okay? That's just the derivative of NP from the thermal equilibrium. Okay? So your thermal equilibrium is where the system want to be. Right? Any extra of that, they will be recombined. But how far they recombine depends the difference between NP minus N9 P9. Because radiative you involve an electron or hole, right? That's why you have both N and P involved. Okay? What is auger? Auger, is the equation. If you remember, the equation is, MP square, MP square. That's basically 1 electrons, right? 2 holes. You see that 1 electron, 2 holes. Okay, that's a 3-particle system. 1n, 2p, right? Because you have n and then p square. P square means 2p, right? So that's basically, if I have 1 electron, goes back to the ground state, I will kick this hole. It's not only just recombine with hole, also I kick the hole to deep levels here, right? It's kind of 2 holes involved. 1 hole is here, another hole move away, okay? What does that mean? That means, you can think about this. When I have electrons goes back to here, I release what? Some photons, right? Photons. But now these photons is not released as what? As photon energy. This one is absorbed by this hole. This hole takes the energy from here and then kicks itself even lower, okay? That's why if 1 electrons, 2 hole, right? 2 hole systems, okay? The same thing you can do is 1 hole, 1 hole, 2 electron systems. Now the whole electron comes here, relieve the energy here. This energy is taken by these electrons, kick itself up to the higher level, okay? So that's why you have what? You have now the derivation is MP minus MP square minus M, right? N9 P9 square, okay? That's what it means, okay? And then this one for it's not 1 electron to hole. If you have 1 hole, 2 electron will be N square P minus N9 square P, P9, okay? That's what it is, okay? That's what's called auger. And I can do the same thing here, find what? Find this one, because 2 conditions can both happen, right? So that's why you have both add together, right? CP, that's what? 2P, 2 holes, CN, 2 electrons, okay? Add together. Then you plug all the, because n equal to n9 plus delta n, and then you get this, and then finally you have the delta n over that Auger red. That's how you get these equations. So that's about the Auger and the recommendation. So to summarize, you know that this is the what the radiative band-to-band recommendation. This one is Auger. Okay, the equation here is complicated. Later you can think about how to simplify that equations. Okay, not later. Right now we can do that. So typically to simplify this equation, what you can do, you can compare the typically majority, right? You have majority carriers, and then you have delta n. Now, for example, if the p-type, if we go back here, uh, let's introduce something new called injection rate. Okay, the injection rate basically is delta n. Okay, if the delta n is much bigger than the majority carriers, either p9 or n9, and then that's called high injection rate. If delta n is smaller than the majority carrier, okay, and then that's called the low injection rate. Okay, that's what it means. Okay, so here's the definition for n-type semiconductors. This is a delta n over, because n-type what? N9 is the majority, right? If delta n is is smaller than 10 times, of 10 times smaller than n9, we call that low injection. If delta n is 10 times bigger than the majority carriers, right? It's 10 times bigger than majority carrier, we call that high injection. The same thing for p-type. If delta n is what? It's 10 times smaller than the majority carriers p9, we call that low injection. If delta n is 10 times bigger than the p9, we call that high injection rate. So basically, compare the majority carrier inside the silicon wafer in the system. If the delta n, the excess charge, is 10 times smaller, low injection. 10 times bigger will be what? High injection. Okay. So here's some example here. I'm going to skip this. You can figure out this since we'll talk about that, right? And then with that, you can simplify. For example, if this is p-type silicon, you have this, right? Because p-type silicon for low injection is delta n is 10 times smaller than p9, right? P-type silicon, p9 is majority. So, and then since this relationship, you can see p9 is so big, right? This one is smaller, this is smaller, much smaller. You can get rid of them, become what? 1 over b p9, okay? That's for low injection, you get this, okay? Now the high injection, what they have is what? Delta n is much bigger than p9. P9 is much bigger than n9 because this is p-type, right? So, and then what you see here, delta n is the maximum. Everything else is gone, right? So that's why you can, ignore the first two terms and then only become 1 over b times delta. 1 over b delta n, okay? Is that clear? Right? So this for high injection, right? And then you can do the same thing here. You can do the same thing for n-type. Basically it's the same. You figure out the relationship with p9, delta n, and n9. And then you simplify this only n9 stays. Same thing here, this is a this one will be delta n stay because there's no answer. Okay, answer. That's what you see. And then with that, these examples you can calculate the. I'll show you here. Right. Since here is what? Here shows the right? The photon generator 10 power 17, right? That's the 100 bigger than the majority carriers, right? So this one is high injection, right? So this is high injection, okay? High injection rate, you use what? This is what material is this, right? This is the phosphorus, right? So this n-type, right? High injection rate, right? High injection rate, high air, right? And then, right? N-type, high level injection rate, 1 over b delta, right? The equation is what? 1 over b delta n, right? So from here, what material is this? This silicon, right? So you like a silicon. That is a silicon, sorry. Okay, that's a silicon. Right, silicon, and then this one is what? Radiative, right? Radiative. So this b is here, right? You use this. You plug this one here, right? For delta n is this, right? Let me move these two. Okay. Delta n is here, right? So 1 over this 4 times 73, times 10 power minus 15, multiply 10 power 17, right? That's what they get. See here? B times delta n. B is this from the table. N is what? Delta n is that, the excess carriers. Okay, you get this about 2.11 millisecond. Okay, 2.11 millisecond. Okay, so that's it. And then similarly, you can do what? You can do for the auger, right? Auger, you also need to figure out, see you have P9 delta n, and then N9 delta n, right? And then if you know the relationship, you can get rid of them because N9, P9 is the maximum, right? Everything else is so small. P9, this guy stay, right? It's gone, right? Then this one, see, it's all small, right? It's gone. So that's why only CP P9 square here. See here, can stay, right? For high never, injection, you have this relationship. Then you plug this. Delta n is maximum, right? Delta n is maximum. Everything else gone. So you have what? CP delta n square plus Cn delta n square. So that's Cp plus Cn and then delta n square. This is your final what? Equations, right? And then that's for p-type. N-type do the same thing, right? You figure out this and then see which one you can cancel. Then that's for low injection. For high injection, you have this and then which one you can cancel. That's how you get for low injection, you get this. High injection, you get this, okay? This is the concept is very similar, okay? Very similar. And then, the similar examples, okay? Now let's take a look at the example. First, you look at this majority carries 10 power 15, right? The delta n, or the excess carries 10 power 17. So this is what? This high level injection, right? And then what material is this? This is also silicon wafers, right? And then what recommendation is this? Auger, right? Auger recommendation. And then this is a phosphorus, so N-type, right? N-type, right? N-type doped, auger, right? Then let's go back. N-type doped, right? And then auger, right? This is auger. And then that's a high-level injection, right? High-level injection, right? Because it's 100 times bigger than the excess carriers. 10 power 17 is 100 times bigger than what? Than the direct carrier 10 power 15. And then use these equations, right? Okay. Then we know what equation we use. This equation, right? This equation we use. And then we need to find the CPCN, okay? CPCN, because delta n we know is 10 power 17, right? 10 power 17 is this delta n, right? Okay, that's delta n, okay? And then find the CP. This is we know is silicon, right? It's also silicon. And then we have what? Auger, right? Auger, right? Cn, Cp, right? Cn, Cp. Then that equation, we know this equation, we know Cn, Cp, we know delta n, and we just plug this number. Wait, look at this 10 power 31, and then 10 power also 31, but 2.8, right? This and this plug to here. That's why you get here, and multiply the delta n, right? Delta n, look at the equation. The question 10 power 17, right? That's how you get this about 263, okay? Now think about, the auger recommendation is much faster, right? 263 microsecond, and then quicker, right? And then the band-to-band recommendation is 2.11 millisecond, right? So band-to-band 2.11 millisecond. So your recommendation, that who happened quicker, who dominate, right? That's why auger will dominate, okay? Auger will dominate. So it's question asks you who will dominate, right? I think this is a thing or photo up, okay? Which dominant will be the quicker one, right? The time is shorter, higher R, shorter, that's will be B, okay? Then if you want to calculate the excess carrier lifetime, you basically, you do that's actually the same toy you have for that lifetime. The lifetime of the carrier basically, is lifetime, the time for their recommendation. Their recommendation is shorter, that determines the lifetime. So basically the lifetime of the excess carrier will be what? Will be this guy, right? So that's because it's, you see here, because he dominant, right? He dominant, so he determines the lifetime, okay? That's it. So with that's we talk about the auger, also the radiative. So next thing we are going to discuss will be the trap osmosis recommendation. What does that mean? That means, if you have trap state, see here we call this ET, the trap state, okay? The trap state, if you have the electron on the top, you have hole in the bottom, right? you can either trap the hole or trap electrons. And then once you trap electrons here, and then see now the energy difference between the electron and the hole is so small. It's very easy for the hole to get there to recombine, okay? Or you can also see the electron can come down here, finally to recombine here, okay? And then in this process depends the trap state. If it's really deep in the center, you may, generate photons. If it's close to the, if this state is close to the valence band or conduction band, you only generate solar energy, the photons, okay? So that's the trap. The trap basically help to assist the recombination, okay? So, and then the trap state assisted recombination is very complicated. Right? If you look at these papers, I'm not going to the details. You will see that, this will be the model, the model for the trap state assisted recombination. Then the P equal to P9 plus delta P, N equal to P9 plus N9 plus delta N, right? That's why you plug that here, you change this, right? P equal to P9 plus delta P, N equal to N9 plus delta M. And then you just plug this to these equations, you figure out this. Okay, this will be final one, you see that, okay? And then there's some other definitions. This is basically equation we talked about before. Early one, I think just before, maybe 20 minutes ago, we talked about this equation, okay? And then you can figure out that when the delta N is equal to delta P, you can simplify that to these equations, okay? That's basically under what? Light illumination, right? Under photo bias, you always have this, how many photons, how many electrons that equal to how many what? Holes, because when electron promote from ground state to excited state, you left the hole at ground state, you have an electron at the excited state. So that's why the delta N is equal to delta P, and then this equation will be changed to this equation. Okay, and then some derivation here, tau P, tau N. This is for tau P, this is for tau N, and there's some other equations. And then if you're not sure what is this tones, each of the tones about, I have the definition here for you. Okay. Due to the time limit, I'm not going to explain each of these, but we do have the total time. This more like outline. I want to show you the concept, the process, how to understand this, and then if you have questions, we can discuss that later. Okay, so here shows the example. This example shows the SRH models. So basically, for mid gap, what does that mean? Mid gap trap. That means they have CB here, BB is here. My trap state happens exactly at this ET. This ET, maybe I should not draw that long. Okay, density is smaller than CB and V. Okay, if this is just mid gap, just midway, and then the midway you can follow this equation N1 P1 because this N1 P1 will be equal to, because this one has EI, right? This equal to EI. When it's equal to EI, that's basically tell you what? That's NI, right? That's NI. So the N1 will be equal to what? NI. N1 is what? The electron, the trapped electron concentration. P1, the trapped hole concentration. Then Y is equal to that, you can plug here, This is EI, right? See, this will be EI. NC multiply this, that's equal to NI, this, okay? So, and then with that, you can simplify this equation equal to what? Pi minus Ni squared, divided by what? Product of tau N plus P plus 2Ni, okay? This will be the equation for mid gap, okay? And then here shows some slides. You can help you to understand, when the recombination is 0, the generation and what? Recombination is the same, right? G is equal to what? R, okay? When this is 0. There's no recombination rate because the generation and then recombination is the same, okay? That's basically NP equal to Ni squared, right? And then if you have the NP is bigger than Ni squared, NP is bigger than Ni squared, then what does that mean? That means you have a lot of extra electron holes. The recombination will dominate, okay? Generation bigger than G in opposite directions. If you have NP smaller than Ni squared, you don't have sufficient, electron hole in the system. You want more generations to, get higher concentration of electrons, higher constraint of holes, so that can reach to this Ni square. Okay, Ni square here is the same as N9 P9. Okay, N9 P9. Because this is intrinsic, right? It's more like a mid gap. Mid gap is kind of intrinsic. Okay, so that's what it's about. So you can also simplify this, low level injections for these models, right? We have these models. You see, we get here. Then now, whenever you think about low level injections, basically you develop these equations. Okay, that's the excess carriers is 10 times smaller than the what? Than the majority carriers. That's what you see. N9 is smaller than delta N is smaller than P9. Okay, and then you use that. You can see N9 P9 cancel each other. They get these equations. Now, since what? Since this pair delta N is bigger than what? N9, so you can get to N9. Here delta N is bigger than that, right? And you can get rid of this part, and then since the P9 here is much bigger than delta N, this delta N, delta N, and that P9 bigger than that delta N, so you can cancel that delta N, right? Cancel this, cancel that. Okay, okay. P9, right? Delta N minus what? N9, right? Delta N plus minus delta N, right? Since this P9 much bigger than this guy, you get rid of him. It's much bigger than this guy, you get rid of him. So that's why top become what? P and delta N. And the bottom you can see the same thing. Since the P9 is bigger than anything, so cancel this, cancel that, cancel that. That's what you see here. P9 delta N divided by 29 P9. That's why your final equation is this. Delta N over 29. Okay. Delta N is N minus N9. Okay. That's how all the concept here pretty simple. You identify the relationship and then you try to simplify equations. Okay. So here shows the example. So as I just showed you, right, for the mid gap, right, this can be the simple equations, simple equations. So we can use these equations here, look, for these questions, right? If you look at this question, talk about the mid gap, talk about mid gap, and then talk about the, buyers. It's 10 power 9. It's much smaller than what? Than the P9, right? This is low level injection, right? This is N9, this delta N, right? Then you basically use these equations, see? N minus delta N, that's excess, right? Excess 10 power 9 divided by what? 29. 29, you actually, that's typically, if you go back, I think right? Oh, it actually give you, right? 29 is 1 microsecond, right? That's 29. That's you get what? Recognition rate about 10 power 15. You can use traditional way, use this way to figure out as well. You can calculate this. But if you use this way, it's simple because you already simplified, equation here. This have your simplified equation. So with that, I think this is something similar here. You just for N-type, right? N-type, and then you simplify this SRH as low level injection, high level injection. You will get this equation and these equations. Okay, this is after you add that relationship, what is the relationship between N9, P9, and delta N? Okay. Okay, and then here shows examples. These examples we can talk about this. Probably I need you guys to read these examples. We can discuss this in that. Okay, with that, I think we finished this chapter. About the recognition and generations. I think now is probably perfect time. We can either take a break or we can start some Q&A. So, Dr. Mukesh.
Yeah, I think
what do we think, Dr. Kumar?
Yeah, we can take 5 minutes break, and then I request Nipun, you can unmute all the participants. This one, they can ask their doubts.
Okay, great.
Sure,
so maybe also help the students in the future. They can preview the slide before they come to the lecture if we have time. You know what? Because we have only like 11 lectures. We try to cover a lot of concepts. So that's why sometimes I go very fast. But they have all the slides, If they can preview, and then also review, they'll be fine.
Yes, we will do this one. Yeah. We will do. So this one, tomorrow's lecture, we will hear tonight this one, then they can go through and then they can come.
Okay, great. Yeah.
Yes.
Nice, yeah.
So now we can take 5 minutes break and then we can start the question and answer session, followed by the tutorial.
Great, great. Mhm.
Yes.
Okay, so I'll be back in 5 minutes. Thank you.
Yes, yes. Nipun, please unmute all students.
Okay, sir.
Yeah, one by one they can ask their doubt.
Okay. Or else sir, they can raise their hand and I will unmute them. Because otherwise, if somebody left their mic open, it would create a lot of
Okay,
noise.
okay, that also you can do.
So, participants, if you have any doubt in any of the three lectures which sir has discussed, you can raise your hand. I'll unmute you. Then you can directly interact with the instructor.
Yeah. Hello.
Yeah, Professor Chow, can we start now?
Sir, I guess he's not here.
Yes.
Maybe
So,
we can wait for 5 more minutes, sir. We have one.
yes.
Kumar, so shall we start back?
Yeah.
Yes, sir. Mr. Sumit, you can ask your question now.
Yes, sir. Yeah. Sir, in perovskite solar cell, the electron affinity and band gap is changed in the simulation study, but normally electron affinity and band gap is constant for any particular material. Please explain me this is to me why.
What's the question again? I'm sorry. You talk about perovskite.
Yes, sir. I repeat it. Uh, In perovskite solar cell, the
Yeah.
electron affinity and band gap is changed in simulation study, but normally the electron affinity and band gap is constant for any particular material. So please explain this to me.
So you said I changed the electron affinity and the band gap yesterday. Is that the question?
No, no, sir, no. In many paper I have shown, sir. So
Okay, okay. Okay, so your question is that the perovskite, because I got lost with your question. The perovskite, have different, different people report different perovskite itself has different structure, right? Different people use different compositions, different structures, and then different elements, right, to make the perovskite. So that's why the perovskite has different band gap, different, conductor band, valence band. Is that your question?
yes, sir.
Okay, and then you talk about the simulation modeling.
Yes, sir. Many paper people some change in simulation study, but normally electron affinity and band gap is constant for any particular material.
Yeah, uh, if you have a particular perovskite, right? Particular perovskite, and then that electron affinity band gap will not change, you know. But sometimes people try to change the perovskite, right? You can have a narrow band gap perovskite, middle band gap perovskite, or high band gap, light band gap perovskite, right? You see that people can tune the perovskite band gap, right? When you tune the band gap, you also change the electron affinity. Electron affinity basically is what? It's from the conduction bands to the vacuum level, right? That's basically EC, right? That's just electron affinity, right? So, so the reason I think I got lost about your question. I'm not sure what's your question about. So can you rephrase your question? The perovskite you can change. You can change your different structures, different compositions, right? Different ratios when you make the materials. Okay. But once you make it, their band gap or their affinity should not change. But another person also
Yes,
claimed
yes.
they made their perovskite, but they will use different element. They use different ratio. They may grow different crystal structures that can also tune the band gap, tune the the pneuma HOMO or the conductor band once band. So they can be tuned. Even the same materials, but at different preparation conditions.
Okay, sir.
Yeah, because perovskite is different from silicon. Silicon is what? You have only a silicon wafer, right? Single crystalline silicon. Everybody talk about single crystalline silicon. That's the silicon. That's the same silicon, same crystals, right? The same single crystalline crystal, right? Unless you may think about the crystal directions are different. But perovskite is just a length of the perovskite. There's many materials involved in perovskite. There's organic, organic. There's organic inorganic hybrid. There's all inorganic perovskite. There's also 2D perovskite, 3D perovskite. When you talk about perovskite, all the materials are different. But that's just because they call that perovskite. That's not the same materials of the perovskite. Okay. So that's probably your question. Okay. So that's different from silicon.
Okay.
Yeah.
Okay, sir. I have, sir, another question. Sir,
Yeah, go ahead.
if activation energy is large compared to the band gap of materials, solar cell material, whatever we have used, so will there be any difference in the performance of the solar cell?
You said, what do you mean the activation energy?
Power to uh, increase the recombination process, I think. Activate means increase the transportation.
You mean okay? The activation energy typically, if you talk about the activation energy, right? If you talk about the charge transport, right? Charge transport, especially in disordered materials, you talk about the activation energy, right? So that the electron can have sufficient energy to hop from this state to that state, right? But typically in the solar cells, we talk about the crystalline silicon. These are band transport. You don't need the activation energy. The electrons stay on the conduction band. They just transport, room temperature automatically, right? That's band transport. All other transport is called, it's more like thermal activated transport because all your state is discrete, right? You have one state here, next state is pretty far away, and then you require the activation energy to transport. That's called disordered materials or amorphous materials. That's typically at high temperature transport is higher, but for crystalline materials like single crystalline silicon, the high temperature you decreases the electron mobility because uh, you create more of this scattering between the electrons with other electrons or electrons between electrons and the lattice. So I'm not sure if you ask these questions. Your question is kind of too general. So did I answer your question?
Yes, sir.
Okay, thank you.
Hello. Hello.
Yes, go ahead.
I think you are saying, sir, something. Please ask.
Sumit,
Yes.
sir was saying, did you get your answer?
Yes, sir. Yes, sir. Yes, sir. Okay, sir. Thank you so much.
Okay. Then you can mute yourself, Sumit. So we have another question from Mr. Kashif Nazir. He's asking, what sort of methods are used for determining band gaps by means of absorption coefficients besides dot plot? And is the methodology dependent on the type of materials?
The band gap, there's typically the band gap you know, especially it depends on what materials you're talking about. For these inorganic semiconductors like silicon, germanium, you can determine that by measuring absorption, you know, absorption spectrum, right? If I go to the slides, let me go back to the slides there, to something we just talked about this morning in the early chapter, right? Let me pull the slides out, okay? When we talk about the direct, indirect band gap materials at the beginning of these lectures, you know, let me share the screen here. If you look at these slides here, you'll see, you know, this one is called absorption coefficient, right? You can also, you know, change this y-axis. You can do just absorbance, right? You know, the absorbance, right? The absorbance basically, you know, you can get what? Visible absorbance is very easily, you can measure the absorbance, right? And then absorbance, you can see, you know, the cutoff, right? See the cutoff here? Cutoff here, the cutoff. Typically, this cutoff will tell you the band gap, right? But this cutoff here is the wavelength, right? The wavelength, you know, the band gap is equal to what? It's TR40, right? If you see the nanometers. If the wavelength is nanometers, okay, TR40, 1240, right? Divided by what? The cutoff. Cutoff, okay? That's not cutoff, okay. I think I spelled the wrong way. Cutoff wavelength, right? But here, since these micrometers, you just the equation change to, you know, 1.24 micrometers. 1.24 divided by lambda, and then you get the band gap. This is typically called optical band gap. You know, in this inorganic semiconductor, silicon, everything here is fine. It's very close. Okay, you can use it to find the band gap. But in organic, you know, in these dyes, conjugate polymers or perovskite probably is somewhere between the organic and inorganic. And then you can measure this band gap through this way. That's called optical band gap. And then there's another way to get the band gap. It's called the electrochemical way. Electrochemical way basically defines the redox potential, right? You find onset for the oxidation, and then you find the onset for the reduction, and then the difference between the oxidation reduction, that's the band gap, okay? That's another band gap called electrochemical band gap. That's typically used for these conjugate polymers, dyes, small molecules, okay? And then that's about the band gap. And then you also ask question about absorption coefficient, right? So absorption coefficient, you know, if you look at the equations, if I go back to the, okay, here's one way, right? Here's one way you can measure the absorption coefficient, you know. You see absorption coefficient equals this equation, you know. This is one way. There's another way you can measure the absorption coefficient. If I go back to, where did I talk about the absorptions? Okay, oh, here, okay, here. I don't have enough information, but anyways, it doesn't matter, okay? So the typically the, you know, if you look at here, this absorption, right, absorption coefficient, right? Then if you can measure the generation rate, and then you know the photon flux, you'll be able to determine the absorption coefficient. Okay, maybe I should do, let's see. So you basically, you know, you can determine this part, right? Look at this, look at this. You can measure how much light intensity at the beginning, incoming, how much light intensity go out, right? That go out light intensity depends on cyclics, right? No. You can see I out over what? I_O, that's equal to what? Exponential, right? Alpha minus alpha D, right? Or alpha D, okay. Now you can get this, you can measure this left side pretty easily, right? And then the right side will be basically equal to what? Equal to minus alpha D equal to log rate, and then I out over what? IO, right? And then this guy, and then you divide by what? And then you divide by alpha equal to log. We can do probably log, right? And let me do this way. You basically just play with this. No, alpha equal to log I out IO divided by minus D. That you see here, you can measure this pretty easily. You know, you can prepare a film pretty easily with a given thickness like 100 nanometers, right? And then you use it divided by that, you get alpha. Okay, that's the way. But this alpha determined as what? Lambda. A different wavelength, the alpha is different. Okay, that's why the absorption coefficient is not flat. It's not flat there. It's wavelength dependent. Okay. I hope this answers your questions. How you can calculate, how can you measure your band gap? How can you calculate from the, measurement? You can also calculate your, absorption coefficient. Okay.
Yes, sir. I hope you have clearly answered his question. We have another question. Yes, sir. He's satisfied. He has typed in the chat box. He has got his answer. We have another question from Himanshu. Himanshu, I have unmuted you. You can ask your question.
Okay, sir.
Yes.
First of all, sir, thank you very much, sir, for such wonderful lecture. And I have two questions, sir. So, as you explained about the perovskite technology, sir, we use a perovskite material there. But, sir, I want to know the other technology like thin film technology where we use cadmium telluride or gallium arsenide, sir. However, we know that they are also a very resilient or very good conductor of electricity. What's the major? Please explain the major reason why uh, the perovskite technology supersede the its cadmium telluride technology. So, are there any significant difference, sir? As we know, the cadmium telluride is also a very good technology. However, it's very toxic, but instead it's a very good technology. So why, sir? What is the main reason that perovskite is so powerful, sir? And my second question is that, sir, when I was reading in the internet, I found the PERC technology, sir, which is same as perovskite technology. It uses the passivation layer. So please explain this.
So what is your second question? The second question, I didn't get it. You talk about the, yeah, go
yes,
ahead.
So I've read somewhere, sir, the PERC technology, so passivation rear emitter and rear cells, PERC technology. So it is also similar to
So
the.
can you repeat what is that technology you read it? What technology you talk about?
Yes, sir.
You talk about passivation. Yeah.
Yes, sir. So they say, sir, they use the passivation layer, sir, to absorb the immense amount of photons of the sunlight, sir.
Oh, you talk about the light management. You talk about because there's a refraction at the surface, so people add the anti-reflective layer on the solar cells, so they make the texture structures, so they improve the light absorption. Is that your question?
Actually, sir, I have not gone through the very detailed information, but I have seen that the PERC technology it is quite in
So
recent.
what technology? Can you repeat what technology is that?
So,
So,
should I clear Himanshu? Himanshu,
yes, sir.
I make it clear to Professor Chow. Professor Chow, he is asking about this mono-PERC solar cell like we are getting in silicon. This is recent technology or modification in normal silicon-based solar cell. So it is called PERC, mono-PERC solar cell, silicon-based. Basically, they passivate and they manage the light emission, and they have a backside solar cell also. So it improves the overall efficiency of the system.
Oh, is that
This
your
is-
question?
So he
Yes, sir.
want to ask that he want to know the comparison between perovskite and monoperc technology.
Oh, here's is that okay? That's the second question, right? Okay, let me come to your first question. Okay, the first question about the cadmium telluride, and then the difference between cadmium telluride and then perovskite, right? So that's your first question, right? Okay, that question, whenever you look at these photovoltaic technologies, right? You look at the cost and then the efficiency, and then also the soft cost for installation, right? And then the other thing, as you mentioned, the toxic, right? Toxic properties, toxicity is all other considerations there, right? So generally speaking, the cadmium telluride, their efficiency, uh, is lower than the perovskite solid cells, right? But the cadmium telluride, the commercialization, for cadmium telluride was very hot about like 15 years ago, 2007, 2008. But nowadays, the kind of it's cooled down, right? It's cooled down. But still, there's a few companies try to, commercialize cadmium telluride. But overall, their efficiency, is not as good as silicon. Is not as good as the perovskite solid cells. That's the one concern. The other concern maybe the toxic, as you mentioned. So since in the market you can buy a little bit, but not big market share for the cadmium telluride, so there's not much commons, to compare with these two. Especially perovskite has not been commercialized there, right? So nowadays, whenever you look at these new technologies, right, there's a lot of suspension. There's a lot of people thinking there instead of the real application, where the data from the real application has not been available. So it's very hard to judge from the application point of view which one is better, okay? But since the market is now dominated by silicon solid cells, it's very hard for these new technologies, solid cells to be compete, from the lifetime, from the cost, from the, customer's acceptance point of view, right? So I'm not sure if I answered your question. Basically, if you compare the different technologies, you look at their efficiency, right? Their cost, their stability, their robustness. These are things you look at, okay? And from that point of view, you can see the advantage of a perovskite over the cadmium telluride, but both of these technologies are still at early stage for commercializations. The market will tell later. Okay. For your second question, I think some of these questions have been asked, earlier, because I do have a chapter later talk about the thin-film solid cells, where you'll see clearly what is the, device structures, what's the efficiency, what's the drawback, for the different technologies when we talk about silicon, when we talk about the thin-film technologies, right? And also for silicon solid cells, people have done a lot of, changes or innovations in the structure, right? And then as Dr. Kumar just mentioned, right? You have back contact solid cells. You have what? You have other kind of solid cells, but still the most common solid cells still the conventional silicon solid cells, but with the texture, the textures, the front contact or the back contact. There's a reflection. So here, basically, you try to improve the light management, right? So the solid cell efficiency, whenever the light get into it, absorb it, that efficiency almost the same. But now you don't want to lose your efficiency by just, have a lot of reflections, transmissions, or other parameters on the surface, right? That's probably where you talk about these nanopores or structures, Since the literature have so many different, the people report so many different things, When you ask questions, it's better to ask more specific questions. You don't want to ask questions so general there, and then that actually I don't know how to answer your question sometimes because it's too broad there. Okay.
Yes, sir. Sir, I know, sir. Thank you very much, sir. Thank you for
Okay,
answering,
no
sir.
problem.
So we have another question from Mr. Said Sadiq. Let me unmute him. Hello.
Hello.
Yes.
Yeah. I'm audible, sir?
Yes, yes, you are. Please proceed.
Yes. Sir, my question is related to the absorption coefficient finding of any thin film material or any bulk material, like the thickness is more than 2 or 3 micron or 4 micron like that. When basically by absorption coefficient, generally we are finding by using the UV visible spectral photometer, and by finding the absorbance, then we are converting this to finding the absorption coefficient. The problem is that when we are finding the absorption coefficient of that material in shorter wavelength, so this gives some different result that actually the reported by the standard measurement, like some other measurements. Like if I'm trying to make the absorption coefficient of the 30 micron silicon wafer. Okay. So for the shorter wavelength like 400, 500 nanometer, this gives different result, which is the actual absorption coefficient of the silicon. And also the next problem is that it doesn't account the reflectance from the surface, because some loss maybe happen. It maybe the absorbance counts the reflection also, because then how we can rectify these things for finding the absorption coefficient? I think my question is clear.
Okay, okay, good. Yeah, so if you measure, the silicon wafer, especially at this low wavelength, that's basically high energy photons, right? High energy photons, and then you can see UV light, somewhere close to UV light, right? I'm not sure if you have substrate, you have glass or something on the surface of the silicon. Since the glass is good, it's very transparent for what? For the visible light, but the glass can also absorb the UV light, right? So that's just a large band gap, right? So that's sometimes I'm not sure. I don't know how you prepare your samples for the silicon wafers. So and when the and also your your UV visible photo spectroscopy. I'm not sure if they have limit, or typically what is range for that measurement, right? Maybe they have from 300 to what, like 1100. But when you get out of the range, and then you make a problem because the system may not support that measurement. Okay, so that's about the first question. I actually don't know. I'd like to know how you prepare your samples, what sample you have, what equipment you use, and then what measurement range that equipment can provide you, and then probably we can help you to figure out where's the problem. And then about the second question, typically when you measure this UV visible, the system should already take care of this reflectance, right? Or you can actually measure this. I think many of these UV visible systems can also measure the reflection, or they cannot measure reflection, but they can measure the transmission, right? They can measure the transmission. So that question, if there's a lot of reflection, then I think the better, you find maybe an emisometer or something to measure the reflection force, right? And then the only thing you need will be at that wavelength, the percentage of reflections, right? And then when you do the calculation, your port may length be less. You need to deduct that reflective part, and then you can calculate your real, absorption coefficient. So that's probably the suggestion I have. If you have the emisometer or other reflection measurement, you should do the reflection measurement for that wavelength you care about, for that, for their absorption coefficient. And then you do adjustment for your measurement from the UV visible spectrometer. Yeah, that's probably my suggestion. Yeah.
Yeah, generally we are using that excellent carry 5000
Okay.
for measuring the absorbance of the thin film
Okay.
or
So
any bulk material.
yeah. So what is the the measurement range there?
Yeah, we have 200 to 3000 nanometer.
200 to 3000. Oh, that's pretty good. That's pretty good.
Yes.
You know. So you know what? Typically when you go to UV light, it's tricky there.
Yes.
So think about you have glass, right? Each time you measure the, absorptions, or even absorbance, right, from the glass. So at the UV side, it's change all the time. You know,
Yes,
that's
yes.
probably, yeah, that's probably the reason. Either the UV light, the light source is not, stable, or there's something happens there. Okay.
So, is there any other alternative to finding the exact absorption coefficient for that material?
Oh, so you only care about the UV light, the large
No, no,
photons?
we are worried about two portion, like for the UV range as well as the infrared, which is above that 800 or 900 nanometer.
Okay. So we actually did not do much research in the UV light or the infrared. So I'm not expert in this field. We care most about the visible light or near infrared, or the photovoltaic applications. That's why we typically don't care much. Even we see some radiation from the UV light or the near infrared, we just ignore them because we care about the spectrum range just between just that's interesting to the photovoltaic, right? So so I don't know the answer for your question actually.
Oh, okay, thank you. So my another question is related to the recombination mechanism,
Yeah.
because I'm doing some modeling regarding the recombination mechanism of the
Okay,
heterojunction
great.
as well as the bulk recombination.
Yeah,
So,
go ahead.
see, so regarding the recombination mechanism, the SRH is mainly affected by the bulk defect as well as the interface defect. So, uh, how to exactly we can calculate or we can find out the surface recombination or the grain boundary recombination?
Okay, that's a good question. So one way, you can, one way you can figure out is that uh, you know the materials, right? I don't know what materials. Are you talking about
Yeah,
silicon or something
yeah.
else?
When silicon is there, silicon.
Oh, silicon. Okay. Uh, you know that the light, right? When you generate these carriers, you can generate the carriers in different regions, right? Because
Yes.
let me show you another slide I have. That's something I'm going to talk about later. Let me pull a new slides. Okay, this is probably next chapter. Let's see which one is that.
Because it is generation recombination, that's why I try to ask this one.
Yeah, just a second. Let me pull the slides there. We do have something to talk about the light preservation at different wavelengths. It goes, different depths in the solar cells. Okay, this one. Yeah. Okay, just a second. I can show these slides here. Okay. So if you look at the slides here, you know, you care about the defect, right? You care about the, recombination, right? Certainly if you want to measure them, right? You care about
Yes.
whether at this interface or this interface or in the deep in the bark, right? So that's how you measure that at different wavelengths, right? Because if you look at the light, they penetrate into the silicon of the device. If you think about this device here, different levels, right? Different levels, If you think of UV light, UV light, their contribution will be basically, happens maybe on the surface. And then when the wavelength, increases, you get deeper into that. So that's typically at these regions, you will see the properties maybe from the N plus. And then the next regions, you will see the property maybe for deeper. You can actually do the similar things to your materials. These are silicon or other materials. You measure the absorption coefficients, at the different wavelengths, which wavelengths it will be go deeper into the materials, right? And then that's means absorption and the surface is not strong. You don't absorb a lot of sunlight, you will not generate a lot of charge there, right? And then when you get to deeper into that, you generate more there, and then you can use that to study the bulk properties. And then you can use different wavelengths that absorb more on the surface to study the surface of interface properties. Or you can also adjust your light intensity, right? And then you make sure all the light, the electron generate just on the surface. And then any property you study there, that will be the surface properties.
In this method, we can measure the recombination for the different regions, like for the interface and the bulk in deep region, as well as in the surface region, like that.
Yeah, you can do that. If you talk about the surface, you can make the two contact just on the surface, right? You shine some light there, some lasers there with no intensity. Now you know because the recombination happens on the surface, right? You just see how much recombination you have there, right? You just study the surface, right? If you want to study the surface, there's a lot of way for you to make it, right? You can just make a very thin film or make the surface properties, right? You don't study the bulk. Did you understand what I said? You can prepare the sample, right? Very thin films, just study the surface. There's no bulk there, right? And then you prepare other samples, with the bulk, right? And then you can, you know what? One sample, just the surface, prepare the interface samples. You have very thin layer of this bulk. You don't have a lot of materials there. Then you can study the surface. For other samples, you do the surface passivation. You remove this, you can control how much defect can have on the surface interface, right? You do the passivation. And then you have thicker films there, you study the bulk, because now you have minimized the impact from the surface or interface, because you passivate that defect, right?
Yeah, my question is also related with how we can include the impact of these recombination in the mathematical modeling.
Oh, you talk about the mathematical modeling.
Yes.
Okay, so what are you trying to model?
Basically, I'm trying to model two things. One is the interface recombination heterojunction between, like a heterointerface recombination, like here the junction between the N plus and P region.
Okay.
The interface between the N plus and P region, and also if the N plus is some microcrystalline material, like generally we are using for the heat solar cell.
Okay.
So if we are trying to model that recombination in the N plus region, okay, if N plus is a microcrystalline structure, so the grain boundary recombination, we are trying to model that one. Then how we can incorporate the effect of the recombination with the grain boundary in the model?
So, okay, now you talk about the interface, right? You talk about the interface, I don't know, the grain boundary.
Yeah, grain boundary, suppose the N plus is a microcrystalline material, so the crystal size is not much perfect, like the crystalline. So there may be the grain boundary between the two grains in the crystalline, microcrystalline silicon.
Okay, so when you do the modeling, right? When you do the modeling, do you need to import the thickness of the N plus layer? Okay, what import you will give to your model for your, for your microcrystal structures?
Yes, basically I'm trying to model the microcrystalline silicon recombination. Recombination in the microcrystalline silicon.
Yeah.
Okay.
And then, do you care about the thickness of this, when you do the modeling? See, I don't know what model you're using. You create your own model lab, or you use existing commercial models? Okay.
No, general mathematical modeling by MATLAB and some standard calculation software like that. By using that, no standard simulation, standard simulator we are not trying to use for that one. We are trying to develop the model for the recombination, so that.
So how did you develop the model?
Yes, see, we are trying to model the recombination in the microcrystalline.
I know you try to model the recombination, from what equations, from, I mean,
Yeah.
you have to start from some
Right now we
physical
are
model.
using
What
the
physical model you are using?
SRH recombination model, and how we can modify that one.
Okay, let me go back to there. Okay. First, I do not do modeling. Okay. The second thing, what I can tell you, maybe from the class point of view, and okay, so you talk about the trap assisted
Yes,
something.
yes,
You
yes.
talk about
Yes,
these
yeah,
things, right?
trap assisted the SRH recombination.
Okay. Did you use this model to model your? Did you use this equation, this physical model to do the modeling or no?
Yes, this model, this SRH recombination equation we are trying to use, but see here P and N is totally dependent upon the excess carrier that we are generated. It is a position dependent parameter.
Okay.
So
Yeah.
at the different depth, the excess carrier generation will be different, so it will impact. So
Yeah. So when you do the model, if you use this model now, the question is more clear, right? Now this is the model. If you care about the surface, interface, or the bark, right? That depends on depth. You need to consider because the excess carrier is delta N, delta P is from what? From the light absorption, right? You can see the delta X, right? Delta X is how much. Uh, you can actually simulate model the light absorption of the depth in the microcrystalline silicon, and then you will know how much delta N, how much delta P is there. That's the easiest thing, right? And then your the next modeling, what do you know here, right? Let's see. Maybe you can tell me, what input you put in the model, right? What things you want to, when you use this physical model to do the modeling, uh, currently how do you do, to the model at different depths?
see, for that for calculating that total recombination, uh, total recombination inside the microcrystalline silicon, like N plus microcrystalline silicon, we need to consider the position dependent recombination rate, because this recombination rate depend upon the absorption parameter or excess carrier parameter. So how we can model that one in a more correct way?
You mean in entire model? You talk about the entire, just use the equations and
Mhm.
then
Or is there any modification is required in that SRH, trap assisted SRH recombination model? Is this trap assisted SRH recombination equation?
yeah, this is the one, right? And then I'm not sure. Do you consider this sigma p? Each of these items. Do you use each of these? How do you get assumption for each of these?
Okay, this
You
these are the
you need to know the trap density, right? The density of the traps, right? Where the trap, not only the density, also the trap, the positions, right? And then you need to know the carrier velocity, right? All this, how did you get this input,
okay.
right? See, this is model. You need a port. You need a lot of input. You need a lot of assumption, right? Uh, So I'd like to know the details of your models, and then I can help you maybe understand, how you. Typically, as I mentioned earlier, if you just throw a general question to me, I have no, I don't know how to answer a question. Especially, say, I want to do the modeling for this SRH. How can I improve my model, right? First, I don't know your model. I don't know your material structures. I don't know how you take into the consideration of this interface, right? The reason for me because we do not do this modeling, right? I actually don't
Okay.
know. I can only help you from the basic point of view, the
Okay.
procedures, the steps. If you
Mhm.
just ask me these questions, a very general question. I actually cannot help you. That's your research, right? I need to know more details about your research, and then I can help you how to improve your model, right? You know what I mean?
Okay.
Unless I'm doing the same research as you.
Mhm.
Okay.
Okay, sir. So in future, I will discuss with you, sir. May I discuss with you?
Sure, sure. Yeah, I mean, if you have a specific question, for example, you know your models. See here, I have my interface, my microstructures. I already considered this. The signals up to here. I can calculate. The delta N, delta E here. See here, this part I'm not sure. Probably we can discuss that. I cannot help any student when they have just throw me a general questions, and then ask how to improve a model. Then I need more details. I need to know what is the project. That's details. I need to know this. Yeah.
Thank you, sir.
No problem. Yeah.
Thank you, sir, for such a nice explanation. We have another question from Ankit. Ankit,
Yeah. Hello, sir.
you can ask a
Yes.
question.
My question. Okay. My question related to absorption coefficient. The absorption coefficient basically remains high for in energy range, which is higher than the band gap. But after some range, it again start to decrease gradually. So how can I define it? With my material, I found this decrement up to the zero. So how can I explain this?
So say again, you ask the absorption coefficient.
Yes, sir.
Is that the
Absorption
question?
coefficient.
Absorption coefficient, and then you talk about the band gap. So can you rephrase your question?
Okay, sir. The
Yeah.
absorption coefficient remains high in the energy range, which is more than the band gap, right, sir?
Yeah, of course. Because you have to have this photon energy that's higher than the band gap, and then you can be absorbed. Otherwise, you're just transmit, right? Is that the question?
Yes, sir. But after some range for higher energy, it again start to decrease gradually. So how can I define it, sir?
Oh, okay. Okay, that's a good question. Okay, so you talk about what materials?
Yes, sir.
Yeah, I want to ask you what's the materials because I can explain to you what's okay. What
Sir,
materials do you talk about?
it was a quaternary chalcogenide solar cell observable material, Cu2, Zn, Sn, S4.
Say again, Cu2.
Zn, Sn, S4.
Is this organic, inorganic hybrid or what? I know. Okay, is this inorganic or a hybrid or organic? What is this materials?
It is inorganic, sir.
Is organic or inorganic?
Inorganic. Inorganic.
Okay. So if you look at the band structure, right?
Yes, sir.
You have photons, right? Okay, this is
Yes.
H mu, right? If you have now let's say your band gap is 2, right? 2 eV, right? 2 eV, okay. So only by theory, only the EH mu bigger than 2 eV can be absorbed, right? Okay, because you need to promote electron from here to here, right? Okay, and then there's a hole here, okay. So the photon energy has to be bigger than what? The band gap, right? E photon, right? It be bigger than the EG. You can absorb it, right? That's why, if you look at the absorption coefficient, not only absorption coefficient, also look at here. The one I just talked about, right? Where is it? Oh, that's a slide earlier.
Sir, I think it was on 42 on number slide.
Yeah, 42. Okay, I'm looking for it. Okay. You look here, that's why absorption after the band gap, there's no absorption, right? So basically, if you have photon energy smaller than band gap, they just transmit through the materials, okay? So
Yes, sir.
that's why you have to have the energy larger than the band gap, okay? The other question, even larger than band gap, right? You can see the band structures you know, let me show something else. Okay, maybe this is a good one. Look, you see here, you see these organic materials here, the absorption here, you know, and then reduce it, you know, increase or reduce. They are not constant, right? They are not constant. That's because the band structure can be something like this. Okay, so typically for the inorganic materials, if you have, you know, very high delocalization, very high crystallinity structures, your band will be something like this. Very broad, very broad. Okay, whenever, you know, above the band gap, is everything is absorbed, right? The band is so broad, okay, so broad. That's why you see something, you know, absorption can be something like this, okay? If this is a E, this will be wavelength, okay, wavelength. And everything above, everything has the cutoff wavelength at the band gap can be absorbed. It should be flat, right? The ideal case, everything absorbed 100% flat, right? But it's not true because the density of the state in these regions, okay, these regions may be higher than other density of state, okay? That's why whenever these regions density of state higher, this region density of state higher, you think about this one is higher. From here to here, you see, you know, from, okay, here is higher. So from here to here, you see the strong absorptions. But from here to here, you see, you know, weak absorption. And then from here to there, strong absorption. From here, weak absorption. Depends on the density of the state at different energy level, E. You know, if you think about this, the E, at different level E, that density of state is different. And then that affects the absorption coefficient. So that also goes to theory here, right? You remember we talked about this, where's the absorption? We talked about the, yeah, remember here, we talk about, you know, the probabilities of this electron hole, you know, their probability for them to meet each other, and also the density of state for the whole density of state for electrons. You see that? The density of state is not, you know, uniform, right? Inside at different energy levels. They are different. That's why, you know, you may see some regions have stronger, some regions have weaker, okay? And then typically the density of state here, close to the band gap, is stronger, it's higher, it's more dense compared to when energy density goes even higher there. High. But it also depends, you know, the UV light, as you know, the photon numbers as this UV light typically is less. The number of photons is less than what? Than the visible light. So there's a lot of reason to explain why, you know, sometimes you see this different kind of absorption coefficient distribution there. Okay. I hope that answers your question.
Yes, sir. Thank you, sir. Is this this is the same reason for the 2 or 3 extrapolation point in tau plot?
2 or 3, say again?
Is this the same reason for 2 or 3 interpolation point in tau plot?
I did not get the question. 2 or 3 what? I'm sorry.
Whenever I try to draw the tau plot for this material, I got 2 or 3 interpolation point where I can draw a tangent line so that I can find out the band gap. So is this the same reason?
Yeah, that can be the same reason. If you see the band, I'm not sure if I answered the question right. Is this what I mean here? Your 2, 3. So sometimes, maybe you should. I'm not sure if you can share screen or something. You mean you draw a line here? You see like something like this, 2, 3. Is that what you mean? Same location or different locations?
Repeat your question.
Sir, whenever I try to draw tau plot, I get 2 or 3 points where I can draw the interpolation point, interpolating line. That is tangent line.
You are talking about the JV plot?
No, he's
No,
talking
sir,
about the
tau plot.
UV visible. UV visible.
Okay.
Let me see if I have slides. I probably have something I can show you there. Is this what you mean here? You get one here, or one here. Is that what you mean?
And one more point, between 300 to 400 angstrom, there is again a straight line.
Oh, you get something. Okay, maybe like this. Like this, you mean? One
Yes,
here,
sir. Yes.
one here. Oh, like
Yes,
this.
sir. Yes.
That I think that's probably the reason I just explained. That absorption happens different between different range. Some range you have weaker. You have smaller amount of state density. That's why what happens. Yeah. This one for inorganic is seldom happens, but for organic it's so common. So common because organic what we have here, the conduction band is not exactly like this. You think about this is valence band. You have band 1, valence band at region 2, and then here you have conduction band, 1, and then another one here. You see, there's a gap. This is a gap between them. During this gap, during this gap, okay, I'm sorry. This gap, there's no absorptions there. Okay, there's no absorption there. Or even there's absorption very weak. That's why you see the absorption peak is something like this. Go something like this here. That's what you see there. Yeah. But if you care about your band gap, you need to use the last one here. Okay. You don't calculate other plot, only the last one. Okay. The minimum is the band gap.
Okay.
Even I can show you another plot. I don't have that. I think I removed that to the. Just a second. I show you another thing. Look at here. Look at here. Look, right. This is where you care about the band gap, right? But you can also do absorption here directly. See here. See here. This will be where you see the absorption gets stronger because you have a lot of state, in these regions. You know what I mean there? But in between,
Yes.
their absorption can be weaker, okay? But you care about the minimum band gap, not the band gap here. Even you see a lot of things, you can find a lot of gaps there, but that's not the band gap. The minimum one, the smallest one is the band gap, okay? Yeah.
Okay. Thank you, sir.
Yeah, no problem. Yeah.
Thank you, sir. We have one more question from the participant, Suraj.
Yes, sir.
Yes, you can ask your question now. Please proceed.
Hello, sir.
Hello. Yeah.
May I audible? Sir, my question is, how we can extract maximum current from the cell without resistive loss?
Without what? I'm sorry.
Without resistive losses.
What
How
loss?
we can extract maximum current from the cell without resistive loss?
Or resistive loss?
Yeah.
Resistive loss. Okay, I see. So that's basically, for example, right? I think we talked about this yesterday. For example, you have the top contact, right? For example, if you think about this, also depends on what solar cells you talk about, right? If you talk about the silicon solar cells, right? So the N plus layer, the quality should be very high. The P plus layer should be very high quality. Typically, if you heavily dope this, silicon to N plus or P plus, you bring a lot of defect, right? Because you almost destroy the structure because it's so heavily doped, right? The silicon crystal structure has been changed. Even you have very high current density there because the dope so high, but the mobility reduces, right? So that's why the quality will be important for the N plus or P plus. And then the other thing, the interface, between the N plus, P plus to the top metal contact. That's why you also need to pay attention. And then one more thing here, I think I probably have the slides here. Sometimes people deposit this oxide layer there, I think I have the slides when we talk about, this was yesterday, right? Okay, here. You look here. Sometimes you have. I'm sorry. Let me stop sharing. You see here, sometimes for silicon solar cell, people deposit the silicon nitride there, and then this silicon nitride, the top contact has to go through it. You have to has high temperature, so let this silver or aluminum, these fingers, diffuse back into the N plus, and then you can reduce this resistance, right? But most of the time for good solar cells, that resistive loss is not significant. Okay, the major loss is optical loss. So for reflection, transmission, this kind of problem, okay? So the resistance loss for most solar cells is not high. It's kind of small. So you don't need to worry too much about resistive loss.
Thank you, sir.
Hello, sir. Hello, may I audible, sir?
Yes,
Yeah,
Mr.
Yes,
Jay, we can hear you.
Yes, sir. Regarding the optical loss, generally we are trying to reduce the optical loss by the texturing or by minimizing the reflection from the top surface. So, when we are talking about the bottom surface, what are the mechanisms we can choose to minimize the transmission from the bottom surface so that the absorption can be increased in the cell?
Okay. Yeah, good question. Depends what solar cells you talk about. Typically, I see, some people work on the third generation, like Dyson size solar cells, polymer solar cells, uh, most of the time, you don't need to worry about transmission because of the dyes, the polymers, or even the perovskite, has very high absorption coefficient. Almost all the light has been absorbed because you can simply just do the transmission, right? Transmission, you find out there's, very small amount of light pass through. That can be, ignored, right? That's negligible, okay? So you typically, most of the time, you don't need to worry about the transmission because of your user can increase the thickness if you don't, if you don't know the uh, benefit about, the internal impedance. And then increase thickness a little bit, you can absorb all the sunlight. If for some cases, you do not, you still have some transmission loss, and then you can add reflector back on the back side, right? For example, when you deposit back contact, you can deposit metal. Many of the metal have very good reflections, visible light. Yeah. So that's probably, if you want to reduce the transmission loss, think about the thickness of materials, and then you optimize that thickness, and then you'll be able to absorb most of the sunlight. You don't need to worry about the transmission. That happens in the most of solar cells. Silicon solar cells, organic solar cells, perovskite solar cells, typically there's no issue. That's why the efficiency can be very high. If you do have that, you can, try to add some reflection backside,
Yeah, like the organic solar cell have the sufficient absorption, but when we are dealing with the thin film silicon-based solar cell, then the absorption coefficient of silicon is not much high. So always there will be a high
What
transmission.
Okay, what silicon? You talk about silicon, you have polycrystalline silicon, single crystalline silicon, or
Yeah,
what?
no. The
Which one?
polycrystalline or microcrystalline silicon.
Oh, microcrystalline silicon. Okay. You did measurement, you show there's a lot of transmission.
Yeah, there is a transmission from the simulation. Basically, we are doing simulations. So from the
Okay.
simulation,
So
I've
that
seen some transmission is there from the backside.
okay. Then then you have to think about how to reflect the light back.
Yes. What are the mechanism we can use for the back reflection?
What materials is that a question?
Yeah, what materials or is there any other method? Uh, is there any another way to increase the back reflection?
Oh, you can, there's anti-reflection materials, right? That typically put on top electrode, right? The front contact. And then you can also deposit the reflective layer on the backside, you know, because that one you can deposit, because the backside depends what device structure you're using, right? If the backside is backside if the backside is just N plus, and then directly you have this aluminum or some metal there, and then the metal itself reflect light back. Okay, you don't need to worry about that. And then if the back electrode is transparent, right, and then you can deposit reflective layer directly on that surface, and then you can embed that contact inside the coating. You just leave some space, for the contact, to collect the contact. So that's probably the general way you can do. Also depends what structures, what materials you use back contact.
Okay. Thank you, sir.
Okay, no problem. Yeah.
Yeah. Good morning, Professor Chow. It was very nice talk. I have few queries. So first, I
Okay.
want to ask how carrier recombination affects the performance of a solar cell.
How what? I'm sorry.
How carrier recombination affects the performance of a solar cell.
Oh yeah, it's the recommendation that you talked about, we discussed before, the shunting, right? The shunt resistance. When you have high recombination, the shunt resistance reduces because you have the channel inside for the carrier to flow internal of the devices, right? When the electron hole recombine, it's kind of electron flow from the from the electron side to the hole side, right? So that's internal shunting.
So,
And then
so,
the electron cannot get out of the load. That's it.
so in that condition, we can say that shunt resistance is analogous to recombination process.
Yeah, it is that. Yeah. So most of the time, the shunt resistance is unless you have pinholes, right? Otherwise, the shunt resistance is recombination. Yeah, it
Sir,
is.
my next doubt was how is there any process or tailoring in material that by that we can reduce the recombination of charge carrier or any technique we can use like thin film, bulk, etc.
There are a lot of techniques there. You can just simply measure the, the luminescence, right? The luminescence, right? If the material is radiative, luminescence, and then you can also measure that by measure the trap density, right? You can measure the trap density, how much charge you can store, you can trap in the device. There's many techniques, right? To measure the trap density, measure the trapped electrons. And then if the radiative, you can measure luminescence. If the trap, you can measure, the capacity, the capacitance, right? Because if you trap electrons there, that's the capacitance, right? You store charge there, right? So there are many different ways you can measure, yes.
So in that condition, the passivation will help to reduce the this radiative uh, recombination, or there is any other method to like we if
Okay, there's methods here. If you want to reduce the radiative, basically you separate the charge, right? You want to separate the charge, right? That's why, if you think about the polymer solar cell, they build bulk heterojunction. You don't want the charge stay in the dollar by itself. You separate charge to acceptor, and then it'll be difficult for them to recombine, right? That's called charge separation, right? So typically, the radiative recombination, that means you have very good, crystal structures. You may not worry about the radiative recombination because you can have charge separation happen very quickly. I think the major recombination happens will be trap or cyst recombination. And then for that one, you need to do the persuasion, as you said. You need to, get rid of this defect there.
but
Okay, I
sir,
hope I answered the question. Yeah.
yes sir, but if the radiative recombination is high, in such condition it may turn the heating losses in the system because the release of energy may be in terms of heating.
You mean, what do you mean heating?
Sir, by radiative recombination, the energy released either in form of light or in form of heating?
No,
Like,
no. If you talk about the radiative, that's the radiative radiation, right? That's not heat.
yes.
Typically, that means you emit the light. That's radiative, band to band. Okay.
Okay. So,
So
sir, it will not turn out in the form of heating.
no, the form of heating basically from the treble system. Treble system. That's called, that one uh, but that will not, produce a lot of heat. I mean, the solar cells is not like, I mean, even the sunlight, right? Unless you let it sit in the sun for a long time, otherwise it's not heat up that quickly, right? And then you even you generate the heat and that will emit easily, right? There's nothing to insulate the solar energy inside the devices, right? So most of the time the solar panel got heat up because of the sunlight shine directly there. The sunlight has 50% of this infrared light. The infrared light just heat up the materials, right? That's what happens there. And then, the solar, even you put silicon wafer, right, in the sunlight, it can heat up, that's just because the infrared light absorption there.
So, in which type of solar cell the recombination rates are high? Like we compare the various techniques or various type of solar cells. So,
Oh,
is there?
the recommendation, for many good working solar cells, there are a lot of issues. There's no issue for that. So see, this is class we talk about the basic sense. Unless you have very bad, materials, very bad device, you have a lot of recommendation. For any, working device, recommendation is so small. You don't need to worry about that. You think about Dyson size solar cells, perovskite solar cells, silicon solar cells. These are not big issue for that.
Okay.
The big issue, as I just mentioned, the major issue is reflection loss, transmission loss. These are the major issues. Okay. The recommended loss, all this, the resistive loss, these are small, minor things. I think I will talk about this in the future slides. Maybe next, I'm not sure, maybe tomorrow or Thursday, we can talk about that. Okay.
Okay, sir, if we only talk about silicon-based solar cell,
Yeah.
so in that condition, what kind of recombination is dominating and why? Actually, I have gone through, but ba- uh, I have done my MTech in solar energy, so I have read it many times, but it was not clear to me at that time also that
Okay.
there
Maybe
are three.
I can throw a question for you. Okay. Silicon solar cells, right, it's got absorb almost, half, 50 of the sunlight, right? So not half, not okay. So the question here would be why the silicon solar cell is not 100%, right? So the loss is basically, silicon solar cells, the solmonization loss is the major sense, right? And then transmission loss is the major sense, right? Because you have silicon solar cells of 1.1, EV band gap, right? Any energy has energy less than 1.1 from the sunlight. That's about what, 40%, right? It will be transmitted directly, right? And then solmonization loss, right? Because your silicon has 1.1 EV, right? 1.1 EV band gap. But how
Yes.
about the 2 EV photon counts, right? And then the 2 EV photon count absorbed by silicon, then there's 2 minus 1.1, 0.9 EV energy lost by solmonization loss, right? So the major loss, that solmonization loss, optical loss, okay? All this transmission, recombination loss, these are minor. They're so minor. It's not important, okay?
Okay. Okay, so
Yeah.
sir, one last question. This is
Yes.
a very basic question. I have to clear this doubt. Like we have fabricated a solar cell. For that material, the band gap is fixed. Like once we characterize the sample, we consider that band gap is fixed. But due to some losses, the heating occurs in the sample, and I found that I found band gap is reducing with increased heating of the sample. So in that case, we can do any dynamic study to correlate the effect of heating on band gap or on the performance of the device.
Yeah, your band gap do change with the temperature, right? I think one of my slides shows that, at different temperatures, the band gap change, right? And also the dopant concentration change the band gap, right? So the band gap is not fixed, you know.
So, sir, is there any particular method to identify or dynamic study of this relation with temperature?
Oh, you can just change the temperature, measure the band gap, measure the absorption, right? And then you will see the cutoff wavelength will change. You know, you can do that.
Okay, thank you so much, Professor.
Okay, no problem. Yeah.
Probably we'll take one more question, one last question it is.
Okay.
He's asking, is it possible to learn about the type of transition, and that is direct forbidden, a load indirect forbidden, or a load using the absorbance data?
Say again. Can you repeat the question?
Sir, question is in the chat box, sir.
The
So
chat
what-
box. Just a second. Okay.
Yeah, if you can see.
Oh, is it possible to know about the type of transition? Oh, type of transition. Okay. Yeah, use the absorption data. Yes, you can. But typically, if the absorbance rate happens in the see now, you know, you have infrared absorption. They're typically IR, right? And then you have the UV visible absorption, right? So typically, from the absorption data from one of the slides, you can see that they have 1, 2, 3, 4, 5 process, right? From the there shows the frequency, right? Frequency actually tell you the energy, right? The energy of the photons tell you what? Tell you also the absorption itself, the wavelength, right? The wavelength, the energy frequencies are all the same thing, right? The longer wavelength, lower frequency, lower energy, right? And then from the energy range, you can tell what type of transition it happens, right? Either free carriers absorption, you know, and the intraband absorption, interband absorption. Yeah, you can do that. Yes.
Thank you, sir.
Okay, great. Yeah.
Yes, sir. We cannot find any more questions.
Okay, great. Mhm.
Yeah, participants,
So-
if you have any,
Yeah, some questions you can ask tomorrow too.
yeah,
So it's tomorrow will be the demo. I forgot. When will be the demo for the fabrication? It's tomorrow or Thursday?
Tomorrow is the fabrication demonstration, solar cell
Okay,
fabrication
So
demonstration.
tomorrow I will have the student ready. Okay, great. And then Friday or Thursday is for the FM. Which day?
Yes, sir. AFM is
on 18th February, it is a surface morphology demonstration by F1. It is on 18th. Yes, sir.
on 17th. We have this solar cell
Wednesday
characterization.
or Thursday, right? Wednesday. So tomorrow is the fabrication. Thursday is
Yes.
for the okay
So,
FM. Okay, I
Characterization.
have it in my calendar. Okay, good. Okay, very good. Yeah.
yes, sir. May I request Professor Mukesh Kumar, sir, to kindly proceed.
Okay.
Thank you very much, Professor Chow. It's really interactive session. Actually, I see students are asking so many doubts. That's a main purpose actually for this course, and I hope actually you are also enjoying. So you're getting the same question in your class there, or
Yeah. We get questions, but many of these questions are related to research. But we don't get much questions about research in the classroom.
yeah,
But these are good questions. That's good. I like these questions. Yeah.
that's good.
Great.
So
Okay.
if there is no question, so we'd like to thank you. Mahesh, you want to add something?
So Professor Mahesh has left,
Okay.
I guess. Yes, sir.
Okay. So thank you very much, Professor Chow.
Okay, no problem. See you. Yeah.
And thank you, everyone.
Okay. Thank you. Bye bye. Yeah.
Thank you, sir.
Bye.
Thank you.